If I could ask you a favor, when you ask a question, if you could stand up and speak loudly, or come to the microphones that are scattered in the room, trying to get the speakers to repeat the questions so everyone can hear, and also folks out in the live stream land can know what we're talking about, which is kind of important. I noted earlier that this is not going to be a one-off workshop. There will be follow-up events, and I think some focus on traditional ecological knowledge, how humans have influenced these landscapes all back through history is probably something we really need to focus on doing next in whatever sorts of forums that we put on as a group. So moving on, climate change. A couple of questions have already come up. So we will be focusing on how climate change might be influencing this new normal for us as we go into the next couple of speakers before break. We have Alex Dye, who is a student here at Oregon State University, and they'll be talking about climate change, how it modifies future burn probability, size, and frequency of wildfires in the Oregon West Cascades. So help me welcome Alex. Where are you, Alex? Yep, come on up.
Yeah, well, pleasure to be here today with all of you at this symposium. It's kind of nifty that Andrew got shifted right in front of me because now we're going to go from the past straight into the future. So some of the same themes apply, however, mostly a lot of the variability and uncertainty with reconstructing something that we don't know about, like Andrew was doing in the past. Those things are going to apply in this talk as well. And so what I'm going to talk about is the mid-21st century in the future, so about 30, 40 years from now, and looking at how if we take several different projections, climate model projections of the future climate and feed those into a fire simulation model, how could that change the fire regime that we're seeing today? And those things are changing fast. We've seen it in the last several years, the last several decades. So what could that look like in the future? And so when you saw that this was going to be talk about the future, I hope you weren't expecting me to predict the future for you. I'm not a fortune teller, so I don't know what the future is going to be. If I was, that would be fantastic. But since I'm not, we have to do science, and we have to figure it out by looking at different versions of the future and what could happen and why and what that means for us and for our plans regarding fire. So we don't have a crystal ball. Instead, we have a bunch of different model projections of the future that tell us, based on various research teams' as best science, what they expect the future could be in 30, 40, 50 more years. And depending on what model, we can look at futures that are extremely more hot and extremely more dry, anywhere down to a little bit cooler and a little bit wetter, or a little bit cooler and wetter in the winter, extremely hot and dry in the autumn, and any combination of those in between. And so in this case, we're wanting to take these different climate projections of the future in the mid-21st century and compare them to the contemporary fire regime, which in this case we're considering 1992 to 2020. And so that's a really tiny slice of the contemporary fire regime, especially in comparison to the 800 years that Andrew was just talking about. But it's also the period where we have really robust records of point locations of ignitions, of weather, and spatial patternings of fire, et cetera. So we take a bunch of these different climate versions of the future. In this study, I'm going to take 12 of them, and these are projected by things called GCMs, which are our global climate model that projects climate in the future and based on our understanding of the global climate system. And we can come up with these different projections. And I'm going to take 12 different of those and feed them into a fire simulation model. And in this case, I'm using the model that's called FSIM, which is often used for evaluating present-day management and suppression, and highly valued resource type scenarios. So we're going to just change the climate input into this model and see what could happen if we get this variety of climate in the future. So instead of a single crystal ball, unfortunately, it's going to be a lot more complicated with that, and we're going to have 12 crystal balls. All of them have some different type of climate associated with them into the future. Hot, wet, cool, dry, any combination of these. Fortunately, though, because like I had mentioned earlier, many of these GCM models have been tested and calibrated to contemporary and or historical conditions, and some of those are known to perform better than others, especially for the western Pacific Northwest. And so there may be some kind of, if it performs really well to the present day conditions, maybe that gives us a little bit more confidence in what's happening in the future. So that's why some of these balls are a little bit bigger than others. Maybe there's some situations that we could give more weight to. But still, there's really no specific likelihood assigned to any of these individual climate scenarios, and keep that in mind as we go through. So I do got to go and be a little bit boring for a second and just tell you about the climate, the fire model that's being applied here. This one is called FSIM, and there's a lot of things that we have to keep constant in order to do an experiment like this. And so FSIM will take in it takes in fuels. For that we use land fire. It takes in historical ignitions, and from this we get a spatial points database for the last 30 years. And it'll do it'll take that spatial probability of where those ignitions occurred. And then most importantly, for our experiment here, it will take climate and weather, and specifically ERC, which is energy release component, and that is a combo of humidity, precipitation, temperature. That's been shown to be really robust relationship across the western U.S. in terms of its relationship with fire occurrence and spread. And it'll take those items and put it into a fire spread algorithm and then output things like burn probability, fire frequency, fire size, and fire seasonality. And so important in this experiment that I'm discussing today, there's a lot of things in here that could change. There's a lot of inputs here, and we're only changing climate. We're only changing these ERCs. Because and you'll see how much variability comes up when we just use ERC. And if we changed everything that mattered, we would be left with probably 12 crystal balls that were just shattered all over the room with nothing to. It'd be really, really difficult to unpack that. Okay, so objective statement. Reiterate, we're going to feed FSIM with climate, specifically ERC, from 12 different global climate models that we've selected for this study for the western PNW region. And I've done this for 5 ecoregions. We've got the Olympics and the Washington North Cascades, Washington West Cascades, Oregon Coast Range, and the Washington West Cascades. And we're going to produce some components of how the future fire regime could change in the future relative to today. These are these burn probabilities, fire size, and frequency. And I also have seasonality, but I'm not going to have time to get to it. But I have slides at the end, so if you're interested in what months fire might occur in the future, you can ask that as a question, and I'll pull it up. All right, here's our 5 ecoregions. And what I'm showing on this slide, you got on the y-axis, your projected change in percent burn probability. So that's the change in burn probability as a percentage of the contemporary, and that contemporary record is 92 to 2020. So everything from 92 up until post Labor Day fires is what we're evaluating changes relative to. And burn probability is to unpack that term a little bit more, it's a percentage. So if you see a burn probability of 0.05, for example, that would be a 5% chance of that pixel or that region burning in any given year. In other words, that's about one burn every 20 years. And so what I'm going to do here is just leave this slide up and cycle through our 5 ecoregions. Key things to look at here is each of these points, each of these dots is a result from a global climate model that I put into FSIM. And so look at how much variability there is there in these points. These are just 12 of these simulation models. And you have variability that's 5-10-fold even per ecoregion, which is huge. And I think that's one of the points I want to emphasize here is it's the name of the game is complexity and uncertainty. We can take medians of each of these or means of each of these, and that's what those horizontal black lines indicate the median of all 12 of the results. But the spread around those medians is just humongous, and we have a lot of uncertainty into what the future holds. However, bracketing like this it's just extremely useful because it gives us a sense of the complexity that we can see in the future. And if we know that this is our range, we can adopt a little bit of a mindset of resiliency to prepare for systems that can handle anything within these ranges, anything from a whole lot more fire to less fire to a relatively small change. And so that's one thing I want everyone to keep in mind as we go through this figure is that just the range in these dots is huge, and I think that's the whole point. And that's, I think, what one of the take-homes is through here. Maps, we have, these are burn probability maps. So for what I'm going to be showing here is that the historical, so this is just what we mapped based on the last 30 years. So this is the relative that we're comparing against, and then the future over the mid-21st century time period. And so that future map on the right is equivalent to that horizontal median line in the box plot. So this would be the median of all 12 of the simulation outputs results. So starting with the Olympics, which is a completely interesting one because of it's the lowest fire frequency and fire size and burn probability of any of these 5 ecoregions, but has humongous percent change. So the fire regimes in the future could be entirely different than they are now, is what that's being said there. Washington North Cascades, this is another one that just has extremely high percent change, as you can see through the box plot, and also extremely high variability, anywhere from an over 1,000% change to even a negative change. And so some of these scenarios, some of these climate scenarios, like I was saying, are actually not projecting hotter and drier. And so it's interesting to see what that kind of a scenario could do to fire. And like I was mentioning earlier, these some of the different GCMs, maybe there's a little bit more confidence in how they replicate contemporary conditions. That's what those star points versus the solid points are. This is just based off of a study in 2013 for the Pacific Northwest that ranks some of these in terms of their replicability of historical conditions. And so, interestingly, a lot of those ones that fall in the top half of those rankings are near the top of this box plot, indicating huge changes in burn probability. Here's down at the Washington West Cascades. And so in these maps, really anything yellowish green and higher is considered relatively high. And then the Oregon Coast Range. And finally, Oregon West Cascades. And you can see here, this is clearly where we have the highest simulated burn probabilities, but in terms of percent changes, it's of the 5 PNW ecoregions, it's lower down. The percent changes are not quite as large. We can also take fire size and fire counts out of this. And so on this figure, what you're seeing is on the y-axis, the number of fires per year, and on the x-axis, average fire size. And these are based on the fire model simulations. So with a single simulation of the fire model, we're basically replicating 10,000 versions of the same year, and then calculating these statistics such as how many fires are simulated in each year, what's the average size of those. And so you've got the average number per year on the left, and then the average size on the right. And so I'm going to just populate this graph with each of those 5 ecoregions so you can see how they compare to each other. Again, each of these points is an individual simulation result based on a different climate change projection. So keep in mind that just how that variability plays out, and then that star point is the contemporary conditions that's being compared to. So here's the Olympics, and then Washington North Cascades. This is interesting because a lot of the future change is occurring in terms of fire frequency. A lot of the dots are above the star point on the y-axis. You have Washington West Cascades. And then Coast Range, another interesting one with the more flatness of the curve, which shows that a lot of the changes seem to be happening in terms of fire size, changes in fire size rather than frequency. Oregon West Cascades. And then finally, put them all together to see how they look together. So quite a big spread in what we're seeing with possible changes to fire size and frequency in the western PNW. So climate, and again, this experiment, climate only, but there's a lot else that we know is going to change in the future, and we don't, this, during the first speaker, we saw that slide where he had mentioned that 2021 was, 11,000 something like 11,000 acres burned, and so every year that goes by, the work is just getting more and more obsolete even. So things are changing, and climate is changing as well. But there's a lot else that we haven't even looked at. So fuels. We know fuels are going to change. It's not going to remain the same landscape forever in the future. There's going to be vegetation climate feedbacks, and you're also going to have vegetation fire feedbacks. So those are going to change up everything we see here and contribute to more variability. You have changes in ignition patterns. Like we know the ignition patterns that we've seen from 92 to 2020 are not going to be how it's always going to be in the future. It's convenient to keep them that way to isolate how climate alone could impact the fire regime in the future, but we know it's not going to be the case. There's going to be changes, could be changes in population patterns and how that relates to where fires are getting ignited. There could be changes in lightning emissions related to climate also, or infrastructure. New roads and a lot of the human-caused fires are related to different patterns of human infrastructure. Management techniques, how forests are decided to be managed and for fire or other things other than fire, all that could change how fire is working in the future. So here we're looking at climate, but we know it's going to be more than climate. And there's a lot of work to do in unpacking the true variability and getting a sense of what's behind all of those crystal balls. Okay. I'm going to wrap that up and can take about 5 minutes of questions. Yeah, 5 minutes of questions.
Very good. Is the increase in the number of fires, is that the number
Yeah, so he asked if it's the change in number of large fires is what we're seeing. And so, yes, I am not simulating anything under 240 hectares. So all of these statistics are 240 hectare fires and above.
How many acres is that?
100.
Wondering if you could go into, you said that not all the features are hot and dry. So could you talk a little bit more about that variability and unpack that a little bit? Because all the GCM features have increasing temperature.
Yes. So Becky asked if I could unpack the variability in climate in the future, because I had said that not all of them were hot and dry, but nearly all of the climate models do project warmer temperatures. And yes, that's correct. Most of the models do project warmer temperatures, but there's more to just heat in terms of what produces ERC and then translating into fire, as well as when that warming occurs. For example, a quadrupling of January temperatures might not have quite the same impact as a quadrupling of August temperatures, for example. And also when those changes in temperatures coincide with increases or decreases in precipitation or humidity, for example. So some of these models that are cooler and wetter actually might be warmer and drier in August, and a lot of that, what we're saying is cooler and wetter, is happening in months that aren't quite as important to fire. Yeah.
Thanks, Alex. So you reported results on a 30-year time frame. Makes sense. I'm all for it. I guess I'm wondering, did you look at year-to-year variability or any sense of what a really rough year would look like versus a really easy year in that 30-year period? Is that something that you can get at from data?
Okay, so Thomas asked if I was looking at any year-to-year variability, and also follow up with what would a really rough year look like versus a normal year. One clarification about the model is we don't simulate chronologically. So it's not 2040, 2041, 2042, 2043, et cetera. It is 10,000 versions of the exact same year. So it's 10,000 versions of what could happen in that same year with this statistical distribution of climate and fire things that we feed it. However, it is possible to pull out one of those iterations of the simulations to see like what would be the worst version of this year. Haven't done that yet, but yeah. Okay, in the back. Right. So what's that? Yeah. Could you? Yeah, I think what I heard was, is there any incorporation of fire vegetation feedbacks in the model?
Yeah, I understand that there can't be at this time.
Right.
But I'm wondering, since you presented it by ecoregions, if you can speak to what you might expect for those probabilities with that fire feedback actually accounted for. That's asking a lot of you right now. You did have that crystal ball.
Right. Yeah. Well, my crystal ball shatters when it comes to fuels. But yes, it's an extremely valid question, and something that we are all thinking about. It is in some ways a little bit ridiculous to not even consider fuels or to even consider that the fire's going to burn and then the landscape's not going to be the same after that. And we're in this framework to do this experiment this way. We're stuck with this. We want to look at just what is going to happen to climate, and that climate is always going to be dealing with the same fuelscape, which, like you mentioned, and is just not going to be the same. It's going to change, and it's going to change following fire and following climate. So I wish I could answer that question a lot better than I can. Okay. Well, thank you.